All right, so we want to do one more example before we look at the next type of improper integral. And this is a really important example, so important that we're going to state it as sort of a theorem down here after we work through this. So for what values of p is the integral from 1 to infinity of 1 over x to the power of p dx convergent? Okay, so what I'm going to do to figure this out, remember p is a constant and x is my variable. I'm going to rewrite this in this form. The limit as t approaches, we have infinity here, so t is approaching infinity, of the integral from 1 to t, and then I'm going to write this as x to the negative p dx, okay? This is the same as the limit as t approaches infinity of, I add 1 to my exponent and then I divide by whatever that new exponent is. So that becomes x to the 1 minus p over 1 minus p is what that would equal, okay? Now, let's think about this limit for a second. We're going from 1 to t. One thing I could do, I have 1 minus p, which is a constant in the denominator. I can pull that out. So let's call that 1 over 1 minus p. And then I have the limit as t approaches infinity. This is now just x to the 1 minus p. And when I plug in my values here, t to the 1 minus p minus, plugging a 1 in for x to the 1 minus p is just going to equal 1, okay? So the goal here is not to necessarily get an exact value for this. It's to determine whether it's convergent or not. And the variable now is this t. That's the thing that I'm having approach infinity. Depending on what this exponent is, this limit, the limit of this guy right here, is either going to go to infinity or it's going to go to 0. It's only going to be one of those two cases. It's going to go to infinity if 1 minus p is greater than 1, okay? Greater than 0. I meant to say greater than 0. So that means if this 1 minus p here is a positive, meaning I have t to a positive exponent, then as t goes to infinity, that power function is going to go to infinity, and so all of this is going to be divergent. If this is less than 0, then this can be thought of as a negative exponent, which means I could write it as 1 over t to a positive exponent. That means I'm going to get a really large denominator as t goes towards infinity, which sends this thing off to 0, and this thing would be convergent. Okay, so let's focus only on when it's convergent. It's convergent when 1 minus p is negative, less than 0. Now, you might also be looking at this and thinking, well, what if 1 minus p is equal to 0? Because then I have t to the 0 power, which is equal to 1. 1 minus 1 is 0. That's a finite number. Doesn't that also give me a convergent integral? And the answer is actually no, because if if 1 minus p is equal to 0, that means p was equal to 1, which means I would have had the integral from 1 to infinity of 1 over x here. But that integral does not have this thing as an antiderivative. It has the natural log function as an antiderivative. And we've actually done that improper integral already. It was our first example. We've shown that that is a divergent integral. So we know that this can't equal 0 because we've already dealt with that case. It has to be less than 0 if this is going to be convergent. This is the same thing as saying p is greater than 1, solving this for p. Okay? We're going to restate that down here as sort of a theorem. So if I have an integral of the form 1 to infinity of 1 over x to the power of p dx, this improper integral is only convergent when p is greater than 1 and will be divergent any other time, whenever p is less than or equal to 1. That's an important result to remember. Okay? Let's go ahead and talk now about the other type of improper integral where we have discontinuous integrands. And specifically, we're talking about integrals over an interval a, b, where there's some value in that interval where f has an infinite discontinuity, which means graphically it gives us a vertical asymptote. And we're going to think about this in three different little sub-cases. One, if that vertical asymptote occurs at the right endpoint of my interval AB, so at B. One, if it occurs at the left endpoint, vertical asymptote as we approach A. And then finally, the case where we have a vertical asymptote somewhere between A and B. So like this value C here, I have a vertical asymptote there. This red box down here is going to tell us how to deal with all three of those cases. So if f is continuous on the interval A, B, where B is not included, but A is, that's where we have a discontinuity at B, like this one, and we're going to assume it's an infinite discontinuity as well. Then this integral, the integral from A to B of f of x dx, is defined to be the limit as t approaches B from the left of the integral from A to t of f of x dx. Notice it's the same idea as the previous case, where we replace the part of this interval that has an issue. So B, our function's not even defined at B, so we can't actually plug B into an antiderivative for this. But we can replace that B with a t and then take a limit as t approaches B from the positive or negative direction. So basically, graphically, what's happening is this t is getting closer and closer to B, but from the left, which is giving me more and more of that area as we approach x equals B here. Okay? So notice we're turning it into a one-sided limit. Similar for a case where we have an infinite discontinuity at A, my left endpoint, we would take a limit as t approaches A, but this time from the positive side, so from the right, of t, the integral from t to b of f of x dx. So that's this case here, where t is approaching A, but from the right, accumulating more and more of that area. Finally, the third case is very similar to what we saw with integrals from negative infinity to infinity. If the discontinuity occurs somewhere between A and B, say at some number C, then we split this into two integrals, one from A to C, and then the next one from C to B. Each of these are going to be improper integrals of one of these types. And so we check both of these using these definitions to see if these integrals are convergent or divergent, which means the same thing that it did before. If they're both convergent, then they both have finite values. We add them up and we get our answer to this original integral. Let's look at a couple of examples. So for our first one, I'd like to evaluate the integral from -1 to 2 of x over x plus 1 quantity squared dx if it's convergent. Or I want to show that it's divergent, okay? So in order to do that, we have to look at this and recognize it as an improper integral. It's a little bit harder to spot this time because we don't have an infinity symbol anywhere. In those previous examples, when you see that infinity symbol, you know immediately that you're looking at an improper integral. But here, if you're working too quickly, it's easy to lose sight of that. The issue here is that my lower limit of integration, -1, if I were to plug that into my integrand, I would have a 0 in the denominator here. So that tells me that this function has an infinite discontinuity when x is equal to -1. That means I have to handle that this way. We take a limit as t approaches that -1, but from the right of the integral from t to 2 of x over x plus 1 squared dx, okay? To evaluate this, I would probably want to use a u substitution. So for example, if I were to set u equal to x plus 1, then that's going to give me du equals dx. So I see the x plus 1 down here. That's why I chose it. It's in parentheses. Here's my dx. The thing that I'm not accounting for here is this other x right here. But that's easy to deal with if I subtract 1 from both sides of this. U minus 1 is equal to x. So that means that x right there can be replaced by a u minus 1. So now what do we have? The limit as t approaches -1 from the positive side. we do need to change our limits of integration here. So this t is an x value in this integral. We want this lower limit of integration to be a corresponding u value. And the relationship is that my u's are equal to my x's plus 1. So I add a 1 to that, t plus 1. Same thing here, 2 plus 1 would make 3. Okay, now let's look at what happens to our integrand. This x becomes u minus 1. This becomes u squared. And then my dx becomes du. This is better written this way. So t plus 1 there, 3 there. U over u squared is the same thing as u to the negative 1 power. Negative 1 over u is the same thing as minus u to the negative 2 power du. This would be equal to the limit as t approaches negative 1 from the positive side of what? So this 1 over u, its integral is the natural log function. Natural log of the absolute value of u, although that's actually going to be unnecessary because, again, this value, as t approaches negative 1, then t plus 1 is approaching 0, but from the right. So this lower limit of integration, when I plug it in, can only be positive. That's a positive as well. So u is only going to be a positive number. The absolute value sign is kind of unnecessary there. And then I'm going to have plus 1 over u. That's going to be this antiderivative here from, we said t plus 1 to 3. Okay? This is equal to the limit as t approaches negative 1 of, let's see, 3. If I plug a 3 in, I get the natural log of 3 plus 1/3 there, minus, in parentheses, the natural log of t plus 1 plus 1 over t plus 1. And this is, again, that's from the positive side there. Okay? So now I have to deal with this integral. Okay? So let's think about what we're looking at here first. So here, if these are finite numbers, these are constants. They're not really affected by that limit. I really need to know what's happening with these two limits right here. As t approaches negative 1 from the positive side, then t plus 1 is going to be approaching 0, because that negative 1 is going in here for that t. But from the right, so we're approaching 0 from the positive numbers. That the natural log function, as you approach 0 on your x-axis from the right, it has a vertical asymptote that goes down to negative infinity. So this is going towards negative infinity. This is doing, what's happening to this guy? I'm approaching negative 1, but from the positive side. So that means I'm plugging in numbers here that are getting closer and closer to negative 1, and but from the positive side, meaning I'm using values that are just slightly larger than negative 1. Things like negative 0.9, negative 0.99, negative 0.999999, so on and so forth, right? So for that, in order to evaluate this, I would think about this denominator as getting very small. It's approaching 0 because I'm getting close to negative 1 plus 1. But these numbers are just slightly larger than negative 1, so that this is approaching 0 from the positive side. That means this thing is approaching positive infinity, okay? Now, how do we deal with this? This is an indeterminate form of the infinity minus infinity type, and we can use L'Hopital's rule on this as well. And actually, I'm going to have to do that in my next video because I'm seeing that I'm running out of space here. So in part 3, we're going to finish this example, and then we have just a little bit more to look at before we're done with 7.8.